Hello to everyone, and thanks for having me here. Today, I'm going to talk about data sharing upon request and statistical consistency errors in psychology. It's a relationship that has been studied before by Jelte Wicherts and colleagues in 2011, and we conducted a replication and follow-up study. So let's see, yes. So on the one hand of the relationship, we have data sharing, more specifically data sharing upon request. Wicherts and colleagues, they requested data from 141 papers published in 2004 in 4 APA journals. They did this because they wanted to reanalyze the data to check the robustness to outliers, but they only received data from about 20% of the papers. And then about a decade later, Van Bamel and colleagues, they did something pretty similar. They also requested data, this time from 394 papers published in 2012 in 4 other APA journals. And this time they did it for a Bayesian reanalysis. They wanted to see whether they would get to the same conclusions. However, they also only received data from about 38% of the papers, which is an increase compared to Wicherts and colleagues, but not that much, certainly given that in the meantime, the climate has been changing and the replication crisis was there in psychology. So this was a bit weird, but I must say these studies are already getting a bit old. So there are also newer studies on data sharing, and we see, for instance, that initiatives such as data sharing badges really help to increase data sharing. However, data are still shared rather infrequently because there are many barriers such as ethical constrictions, practical constrictions, but also fear that your data will be scooped or that errors might be found. So on the other hand of the relationship, we have consistency errors, and consistency errors are a type of reporting error. So it means that you find these errors on the paper level. You don't need raw data to detect these kinds of errors. So what is a consistency error? If you conduct a statistical hypothesis test, then you usually report a test statistic and the degrees of freedom and the p-value. If you have 2 out of 3, you can calculate the third. So the idea is that based on the reported, in this case, F statistic and the degrees of freedom here, you can recalculate the p-value. So here, in this example, the recalculated p-value is equal to 0.0035. But in the paper, the authors reported a p-value of below 0.001. And so this is inconsistent, and this is what we would call a consistency error. Then there is also a specific kind of consistency error, and this is what we call in this context then a decision error. And here, the recalculated p-value and reported p-value are not only inconsistent, but they also lead to a different decision. We assume here that alpha is equal to 0.05, but here we have another example. The F statistic is 3.07. The degrees of freedom are 1 in 88. The authors reported a p-value of 0.02. If we take alpha to be 0.05, then we would reject the null hypothesis. But if you then would recalculate the p-value, you find here that it's equal to 0.0832, which is larger than 0.05, and then you would accept the null hypothesis. So why is it interesting to look at these consistency errors? Well, Wicherts and colleagues, they reported in their original study that these documented errors are arguably the tip of the iceberg of potential errors and biases in statistical analysis and the reporting of statistical results. But it's also important to note that these Inconsistencies do not necessarily indicate questionable research practices. They could be just mere typos. If you make a mistake in the degrees of freedom, of course, you will get a different p-value, for instance. And the absence of consistency errors is no guarantee for the absence of underlying errors. For instance, if you made a mistake in pre-processing your data, this won't be a consistency error in your paper. So what I will talk about is first the original study by Wicherts and colleagues on this relationship, and we also reproduced their results, and then we also conducted a small multiverse analysis to check the robustness against alternative analytic decisions. And then we conducted a replication study with data we got from Van Pamel and colleagues. And also here we checked the robustness against alternative analytical decisions. Then I will discuss the results and end with a conclusion. So first of all, in the original study, Wicherts and colleagues, they narrowed down their sample to 49 papers from 2 journals. And this subset, the data were shared for about 43% of the papers. And they manually extracted unique triplets of T, F, and chi-squared statistics with p-values below 0.05. Then all p-values were recalculated and compared with the reported p-values, and I did this in Excel. And they found about 4% consistency errors and 1% decision errors. From their study, we selected 2 hypotheses that we would reproduce and later replicate. The first one was the relation between the number of consistency errors and data sharing. That did this with a negative binomial regression with a log link and a robust variance estimator. And so they estimated that if the data were shared, the expected log count of consistency errors decreases with 0.83, everything else taken constant. Because it's hard to think about this in log counts, yeah, we also took the exponent of this regression weight, and then you could say that there is a degree of 56% in consistency errors if the data are shared. The second hypothesis that we selected was the relation between the presence of decision errors and data sharing. Decision errors were not so prevalent in the data set, so this is why they did not fit the negative binomial model again here, but they constructed a 2x2 table, and then they did a Fisher's exact test, which rendered a statistically significant result. But you can also see in the 2x2 table that none of the papers of which the data was shared had a decision error. So you see the 0 here on the right at the bottom. So as I said before, we reproduced these numbers, and we used the categories suggested by Arner and colleagues to evaluate this reproducibility. They suggested 2 scales, one correctness and the other one is vagueness. First of all, the numbers were correct. We did have to account for a small margin of error because our standard errors were slightly different than the original ones. If we conducted the reproduction in R, however, if we did it in SPSS, just like the original authors did, we got exactly the same numbers. And we also evaluated the reproduction attempt as low vagueness because we requested the data from the original authors, and they shared with us a very well curated data set, so all variables were very clear. And the SPSS syntax was also shared, so it was very clear which analysis they actually did. So like I said, we then conducted a small multiverse. I don't have the time to go into detail about which decisions that we varied, but the figure that you see here shows the confidence intervals of the exponent of the beta weight for the predictor shared for each specification. The one you see here, it means that there is no effect, and you see that all these confidence intervals are on the left of 1. So it means that there are more errors when the data was not shared. There is one thing that is pretty striking here, and that is that the original authors, they used a robust variance estimator in their model, and we did the same thing. But we also varied in the specifications to use the standard variance estimator. And then funnily enough, we got larger confidence intervals. I think this is a bit counterintuitive. And for some of these specifications, this would also render in a statistically non-significant result. So this was a bit weird, but other than that, everything seems to be in line with what the authors found before. We also varied some choices for the second hypothesis. Here there is not that much to vary, so we just also conducted a chi-square test and a g-test. And instead of constructing a 2x2 table, we also just counted the number of decision errors per paper. And we also included an option here to include an exclusion criterion. So then I can move on to our replication attempt. So as I said before, we used the data from Van Pamel and colleagues. So they requested data from 394 papers, and the data were shared for about 38% of these papers. Other than in the original study, we did not manually extract triplets of statistics, but we used an automated procedure, namely StatCheck. It's an R package developed by Michel Nuiten. And we also used StatCheck to evaluate all detected triplets, but all the flagged consistency errors were also manually reviewed for false positives. Because as StatCheck is an automated procedure, it cannot take all context into account. So if there was a false positive because it was a one-tailed test, because of, or instead of a two-tailed test, or because of statistical corrections, then a human would correct for this. And we found about 6% consistency errors, which is a little bit more than in the original sample, and also 1% decision errors. Then, like in the original study, we fitted a negative binomial regression to test the relationship between the number of consistency errors and data sharing. And here you see that the effect is way smaller. Here we would expect a decrease of 12% in consistency errors if data are shared. You also see here that the p-value is way larger. And then for the second hypothesis that we selected, we also again conducted a Fisher's exact test. The p-value here is also no longer statistically significant. And you see in the 2x2 table here that there were papers with decision errors, although their data was shared. We also evaluated the replicability of the results, and we did this by a categorization that was suggested by Lebel and colleagues. They suggested three criteria. First of all, there was no signal, as in our results are not statistically significant. And then second, our results are inconsistent with the original results because the confidence interval does not overlap the original point estimate. And then finally, our estimates were more precise because we had a larger data set. We again then varied some choices here and did a small multiverse analysis, you see that we have way more confidence intervals here than for the original study. That is because we had a couple of more options in the last decision to include and exclude papers and statistics. So that's the reason why there are a couple of more confidence intervals. But what you see here overall is, first of all these confidence intervals shifted a bit to the right. So the effect is smaller, and most of them overlap 1. So they are statistically insignificant. And what you see here is that the estimator makes more sense, as in the robust variance estimator usually gives a bit of a larger confidence interval than the standard estimator. So here it looks more like what we would expect. And then finally, we also varied the choices for the second hypothesis, the relation between the decision errors and data sharing. So again, we included the chi-square test and a g-test. And instead of just a 2x2 table, we also counted the decision errors. Here there are again a couple of more rows because there were more inclusion and exclusion criteria that we could vary. But they all point in the same directions. Mainly all the p-values are quite large. So why are our results so different from the original findings? Well, first of all, this could be just a difference in the papers that were included in the sample. So in the original sample, the papers were from 2004. Now they are the papers we used are from 2012. It is possible that in the meantime, the relationship has changed. So that is one possibility. A second possibility is that there could be differences between journals. And we think this is likely. But there is also another explanation, and maybe this is more important, and that is that perhaps the detection and evaluation of triplets, as is done by StatCheck, is not a very good proxy for how it's done manually. And to investigate this, we looked at the validity check that was done by Nuiten and colleagues in a paper of 2016. And what they did is they ran StatCheck on the original sample from Wicherts and colleagues. And so here in the Venn diagram, you see that most statistics were detected by both what I call the manual check and by the automated StatCheck. So there is an overlap, but you see that still quite a large amount of statistics was only detected by the manual check. And then there were also some that were only detected by StatCheck. So where does this difference come from? As I said before, StatCheck is an automated procedure. It could only detect statistics that were in a standard APA format. So I have an example here of what StatCheck could not detect. Here, the mean squared error is reported in between the F statistic and the p-value. If this is the case, StatCheck cannot detect it. It can only detect the statistic, degrees of freedom, and then p-value in a specific format. So from the moment that something changes, StatCheck will miss it. So that's one of the reasons. And some statistics were not detected by the manual check because they were located somewhere else in the paper and not in the results section, for instance, in the discussion section or in a footnote or somewhere else where Wicherts and colleagues wouldn't look. So now we can wonder what kind of impact does this have? And to get an idea of that, we fitted the negative binomial regression 3 more times. on the statistics that were detected by both the manual check and both stat check. And so here I only show the beta weights. But so first, we ran the model again on statistics that were only detected by stat check and a manual check, but with a manual assessment. And you see here, the beta weight is pretty similar as the minus 0.83 of before, but the effect is smaller, and you see also here that the p-value is larger. So the statistical significance disappears, let's say. But then we also ran it on statistics that were detected by both methods, but this time when they were evaluated by, on the one hand, the default stat check mode, and on the other hand, on stat check with a one-tailed test detection. It's an option that you can choose for. And then you see, and this is quite peculiar, is that the beta weights, they're like reversed, like the sign the negative sign becomes positive. So this is a bit of a weird result. But I can say, I hope that I can say that this doesn't really matter for our study, since we reviewed for we checked for false positives, or a human checked for false positives. So we hope that this does not have a large impact, but perhaps the selection of statistics did so. So I conclude here that for results reported conform APA standards, there is no strong general relationship between sharing research data upon request and consistency and decision errors. So thank you for your attention.
Thank you very much, Aline. So we still have 3 to 4 minutes for questions, if people have questions.
I'm wondering about how you see the world changing. Obviously, you were working with some data collection attempts that go back a few years, but norms have changed fairly rapidly in psychology. A lot more people posting their data, and expectations of data sharing have gone up a lot. How do you think it would turn out if you ran your study now?
Yeah, it's hard to tell, because what I did not include here, because there was no time, is that there also has been a very big study, actually 3 studies reported in one paper by Michelle Nuiten. And she studied quite a large amount of papers and various ways of data sharing. So I don't remember exactly by heart what she did, but I think she compared between, I think she looked at psychological science, and then between papers that did have a badge and didn't have a badge, and then between 2 journals, one with like the recommendation to share, and then the other one that were you involved with this? Okay. So, and then another one, I think with a more strict policy, and also in more recent papers. I think the papers were from 2000. I should look it up. 2016, 2018, something like that. So a bit more recent. But she didn't find any indication of a relationship between errors and sharing. But of course, since she developed StatCheck, she also used StatCheck to find consistency errors in such a large amount of papers, which makes sense. But yeah, if we look at what I found here, yes, I can go back. Yeah, what I found here is that if I would run the same model on the same data, but just evaluate with StatCheck instead of with how you would manually evaluate the numbers, then well, these beta weights, they just reverse. So maybe it has got something to do with the statistics that she selected with StatCheck, but I wouldn't know. So I think it's hard to tell. I don't know if that answers your question.
Yeah.
So we have less than 1 minute for one more question, or if not, we can move on.